Okay, so welcome again. Uh, so today, Seongjeong Kim from the Jilin University will continue his talk on Introduction to Knot Theory. So today he will be talking on Kauffman bracket and the colored Jones polynomial. Yeah, over to you, Kim.
Okay, thank you very much for introduction. Today, let me continue my series talk about the knot theory and relation with three manifolds. Today I will talk about, I will introduce what is the Kauffman bracket and what is the Keller-Jones polynomial. So before that, let me remind what we did last time. Last time, we firstly introduced what is a knot. A knot is a map from S1 to R3 or S3, or precisely a smooth embedding up to ambient isotopy. And here, what is the ambient isotopy? Ambient isotopy is a map from R3 times I to R3 continuous map such that for any T, this is a homeomorphism on R3. And secondly, H something 0 is identity, H something 1 send one knot to another knot. So and the link is similarly a smooth embedding of disjoint union of circles up to ambient isotopy. Then it is known that for any knot or link, we can draw such a figure, which is called a diagram. And by theorem, two links are equivalent if and only if corresponding diagrams are equivalent modulo 3 local moves. Called Master moves. So our goal is to distinguish knots, and to obtain that goal, we study invariants. Invariants are, simply speaking, maps from the set of links to some set up to so. But thanks to the Weidemeister theorem, there is one-to-one correspondence between links up to ambient isotopy and the diagrams up to Weidemeister moves. So instead of this map, we construct this map, which makes this diagram commute. One example is quandary coloring invariant. And another one was not quandary. So last time, and the quandary coloring invariant is an invariant with codomain C is equal to n union infinite, and not under is, in this case, C is a set of groups up to homomorphisms. Isomorphisms. So we show that by using not those invariant, we can distinguish this knot with trivial knot. And figure 8 knots. And the topics which we would like to see, the carbon bracket and Color-Jones polynomial are another invariant of knots valued in Laurent polynomial ring, Laurent polynomials. So before talking about those invariants, let me introduce one more concept of knots, which is called framed link. A framed link, there are several ways to define framed links, but one way is, let me say knot. Framed knot is a map from analysis to R3, which is a smooth embedding up to ambient isotopy. Then, so the framed links is smooth embedding, not S1, but S1 times I. Then they looks like this. So like, of course, they are bent. Such a knot is called framed knot. Of course, in the same time, we can define framed links also in the same way as just disjoint union of the channelers to R3 up to ambient isotopy. But in this time, it is not easy to draw framed links because every time we need to draw such a bands. So we will find another way to express framed links. For that, let me introduce one concept, which is called linking number. Let R be a two-component link, or precisely oriented link. Then for crossing, maybe you remember we can give a sign +1, -1, which is called crossing sign of a crossing C, and we will denote it as G and C. Then the linking number of K1, K2 is 1/2 sigma crossing signs, where this crossing is a crossing between different components. We will sum all signs of such crossings and make it, we divide it and divide it by 2, then it is called the linking number. This is called the linking number. So for example, let's say we have such two-component link. Sorry, yeah, let me draw it. Let's say we have such a two-component link, K1 and K2, totally L. Then the linking number of K1, K2 is 1/2 sigma crossing signs of crossing between different components. So in this case, we have only 2 crossings between 2 components. We do not care about other crossings. Then locally, this part are oriented like this, and this part oriented like this. Then for this crossing, which looks like this, and you can compare with this crossing. So this has crossing sign +1, and similarly, under one also has +1. Then their linking number is +1 + 1 is equal to, divided by 2 is equal to 1. In this case, the linking number is equal to 1. Then why I introduce such a notion? Because for the framed link, framed knot and link, since we have a embedding of analysis, if we consider just boundaries, then this boundary and another boundary, then we can obtain two-component link. So let's say this one is K. And another boundary is K prime. And now we calculate linking number between K and K prime. In this case, how many crossings we have, crossings between different components we have? Then here, 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 and here, here. Then we give one orientation, and then we calculate linking number. Then to save time, let me write directly their sign. In this manner, we have 6 minus 1 and 4 plus 1. Then the linking number is 6 minus 1 plus 4, 1. And this is equal to minus 1. And now, instead of this band, if we draw, sorry, if we draw a knot with integer number minus 1, then this can represent the framed knot, because you can easily reconstruct left part by using this minus 1. Simply speaking, you just draw parallel, but you give such a twist to make the linking number between red and black become minus 1. If you do like that, you can make equivalent framed links from right part. So it is enough to represent framed links by using knot with integer number. So we can see that there exists there are one-to-one correspondence between framed links and links with integer numbers. And sometimes people call this one is framing. And here I have one small remark. When we have such a kink of band, if you make it straight, then actually this becomes like this. Similarly, if you twist this kink, then you will get such a band. So here you need to be careful a little bit. This is here I said there are one-to-one correspondence between framed links and links with integer numbers, not diagram, but links. Then how to represent framed links by diagram, and which local moves are required. So as usual now, we want to represent by knot diagram. But of course, one easy way is, as we did, well, we already draw diagram with integer number -1. But we want to represent it by diagrams without such a numbers. So to resolve such problem, I'd like to introduce one notion which is called blackboard framing. Oh, sorry. Yeah, blackboard framing. Then before going to blackboard framing, why I don't want, it is not that we would like to remove this -1. It is because when you recover frame the links, frame the knots and links from diagram, we draw a parallel, but we need to make such a, how to say, linking between two boundaries. But to be honest, simply speaking, it is not that easy. I mean, not difficult thing, but how to say, it is a little bit awkward things. We don't want to make such a labor to obtain framed links. Then what is the simplest way to draw such a second component from the given diagram? Then it is the following. When you have a diagram, simply we draw a diagram parallel to the original diagram. Then this is called blackboard framing. Then this is related to a knot with which framing number. Let's say the knot is oriented like this. Then to save time, let me, then we have 1, 2, 3, 4, 5, 6, 7, 8. 8 crossings. And their signs are -1, -1, -1, -1, -1, -1, -1, +1, +1. So there are 6 -1, 2 +1. So linking number k prime is equal to 1/2 sigma 2 6 -1 plus 2 1, so -2. So this corresponds to the framed links with integer number -2. And here I have one small remark. For example, when we have such a knot and we draw blackboard framing like this, then the linking number k and k prime is equal to the rider of D. Then what is the rider of D? Is the summation of all crossing signs of D. For example, in this case, if this one is oriented, when you draw oriented knot, you calculate crossing signs, then -1, -1, -1. Then the rider of this crossing is equal to -3. And if you calculate linking number between those two things, then you can find this is -3 actually. Moreover, in this diagram, original diagram is this one, and if you calculate my rider of this diagram, then actually it is equal to -2, which is equal to the linking number between original knot diagram and its blackboard framing. So what we can do from the above observation, if we want to get the diagram corresponding to, for example, a knot with framing 0, then you just need to do such kind of thing. You draw diagram, same with the left one. Sorry. Yeah. Then, if we do not do anything here, then the blackboard framing gives linking number -3, because as we saw in the previous page. But we want to get 0 with blackboard framing. Then what we do? As I said, the linking number between original diagram and blackboard framing is equal to the summation of all crossing signs. And in this case, -1, -1, -1. So to obtain 0, we add 3 more crossings with crossing sign plus, plus, plus. Then if you draw blackboard framing here, then you can obtain a knot with framing 0. So in this manner, you can obtain a diagram corresponding to a framed knot. Then in this case, you don't need to draw any, you don't need to write any integer numbers. But by putting more or putting more kings or deleting more kings, you can control the framing numbers. And then as a proportion, we can prove we can see such a we can prove such proportion. Rings L1, L2 are equivalent. It means up to ambient isotropy if and only if corresponding diagrams are equivalent. Two framed links L1, L2 are equivalent if and only if corresponding diagrams are equivalent by those three moves. As you can see, those two moves are Reidemeister move. Two moves of Reidemeister moves, and instead of Reidemeister move 1, we add this one. Here, originally, we had such a move, but as we saw in the previous, in the above, such a adding kink or removing kink change framing. But if we do like this, then no. Then what does it mean? Later, you may check by yourself, but simply speaking, if you give orientation, then their crossing signs are different. So if you draw blackboard framing here, then you can see this one is equivalent, the same with this one as a band also. So in some sense, it is reasonable to add such a moves, add these moves instead of Reidemeister move 1. Okay, before going to next topic, do you have any questions, just in case? Sorry. Okay. Actually, it is not easy to see the chat, so
No,
if you do
I'm
not
seeing.
mind.
So if there is any, I'll let you know.
Yeah, thank you. Okay, in this manner, we can define framed links, and framed links can be presented by diagrams without integers, and the equivalence relations are obtained by those three moves. And now, let me go to our main topic, which is called Kauffman bracket. Kauffman bracket is an invariant obtained from diagram valued in Laurent polynomial ring, and this is defined as follows. This is defined by as a map from diagrams to Laurent polynomial ring defined by for each crossing. This bracket satisfy such an equality, and if we have an additional circle, then it is equal to L. By using those two equality, we can obtain such a map. Let me show one example. Let's say we have such a ring, a two-component ring. Then what we do, In the definition of Kauffman bracket, firstly, for each crossing, it satisfies such equality. So firstly, we choose one crossing and then apply that equality. Then, oh, sorry. Here, before, I forgot to say. Oh, sorry. Okay. Here, how this equality, in this equality.
No, Kim, your screen is not visible. I guess it got turned off.
Okay, sorry. Thank you. I was a little bit rushed. So here in this equality, we have a crossing and we remove those two crossings in two ways. Then how we choose? When we have a when we have a crossing, when you rotate over crossing in counterclockwise way, then there are two regions covered by overcrossing and remaining things. And we call this one is A region and this is B region. Then when we open road between A regions, then this is called A splicing. And when we open B regions, open the way between B regions, then this is called B splicing. And now, for a crossing, this equality means this is equal to a linear combination of two diagrams obtained by splicing in by A splicing, B splicing separately, respectively, and then put two coefficients A and A inverse. And we use that relation like this. From this example, we choose one crossing, and then in this crossing, you can find that this one is locally A region, and this one is B region. Then by doing A splicing, you can obtain such a diagram. And by B splicing, we can obtain such diagram. And we put A and A inverse. And then we repeat this one. For this one, there are only there is only one crossing. So here again, we have A, B, B. So we multiply A and the diagram obtained by A splicing and A inverse with diagram by B splicing. And then similarly here also A inverse with B splicing. And now, from the last condition, we obtain if we have trivial circles n times, then A is equal to minus a to the 2, minus a to the minus 2, n. Then this is called, then here in the end, we spliced, removed all crossings, and we just obtain trivial circles. Then we replace it by a to the 2 to the a to the minus 2 square, minus a to the 2 minus to the 1, minus a square minus a to the minus 2, minus a square minus a to the minus 2 square, like this, with respect to number of components. Then by expanding this one, we can obtain Laurent polynomial. And this is well known that this provides invariant under Rademacher move 2 and 3, but not under Rademacher move 1. Then why it is not invariant under Rademacher move 1? It is because if we add kink like this, then it is equal to a to the 3 plus minus 1 d. This one with respect to the crossing kink. So as a corollary, we can get D is invariant for framed rings. But in this level, now this one is not invariant under all Rademacher moves. So what? So we modify this invariant to obtain to make it invariant, to make it to be invariant under Rademacher move 1 also. Then how we do? Actually here, when we add one crossing by using kink, we need to multiply minus a to the 3 to the plus minus 1 with respect to the sign of the kink. From that idea, sorry. Oh, okay, I understand what's the problem. From that observation, we use rider, which we defined before. For an Knot diagram D, rider D is the summation of crossing signs of all crossing of all crossing of D, and this is called the rider of D. And if we multiply minus to the A to the minus 3 WR D to the bracket, then this is invariant under Rademacher moves. And we will denote it by G, K, A. And this is called the Jones polynomial. But this one is a little bit different, with original definition of Jones polynomial. I mean, original value of Jones polynomial. But it can be obtained by variable change. You just replace a to a by t to the minus 1 over 4. And this one is again the Jones polynomial. So by the visual of notation, sometimes people call this one is also Jones polynomial, but originally the Jones polynomial is obtained by JKA by replacing variables by t to the minus 1 over 4. So this historically, Jones polynomial is defined by by using the representation of von Neumann algebra and its trace map. But few years later, Kauffman provided such a bracket invariant, so-called Kauffman bracket, and showed that actually Jones polynomial and Kauffman bracket are related in this manner. So after that, sorry. Several generalizations of Jones polynomial. One family is variable, two variable apply PT polynomial and Kauffman two variable polynomial. And in this case, they are defined by using different relation. I mean, for Homfly PT polynomial, sorry, I do not remember exact formula with the Z. They use such a they define polynomial by using such an equality, and Kauffman two bracket two variable, as I remember, related like this. Sorry, I forgot the exact formulas, but anyway, the one way to generalize Jones polynomial is define polynomials with different equations. And the second way is what we want to do, and which is Color-Jones polynomial and Reshetkin-Traev invariant, which I will introduce next time. So basically, they are defined by representation theory and quantum groups. And it is a kind of generalization of original definition of Jones polynomial. And from here, we obtain Reshetikin, Trief, invariant, and colored Jones polynomial we obtain here. And other ways to generalize Jones polynomial. And our today's goal is to introduce what is the colored Jones polynomial. Of course, originally, the colored Jones polynomial is defined by using representative theory and quantum algebra, quantum groups, quantum Lie algebra in some
Kim, there
sense.
is a question
Yeah.
in the chat.
Let me go. Yeah, no, in bracket polynomials we take right. So polynomial within this. Yes. Actually, it is true. Yeah, it is true. Usually, there is a really good question. On purpose, I didn't say that. Originally, we add one more thing here. If it is just one trivial circle, then we just we add we say it is equal to 1. Yeah, that's right. But no big difference. I mean, just we need to divide by 1. If we define like this, then it's equal to 1. So in some sense, I say I introduce no unnormalized Kauffman bracket, but no big difference in the definition. But yeah, if you so I didn't because of time I didn't say details. But if we define Kauffman bracket in details, then we need to consider such kind of thing. But no big difference. So I just say in this manner. Yeah. And moreover, how to say, as I understand, when we later, I mean, in this talk, I will not cover that part, but when you see the Covano homology, such kind of categorification of Kauffman Jones polynomial, in that case, they use unnormalized version. So, but anyway, yeah, you simply speaking, you are right. Yeah, originally it is 1, but because the difference is just one division by this element, so no big difference. Is it the answer? Ali, is it enough for you? Yeah. Thank you. Yeah, thank you. I also think, do I need to say it? But yeah, on purpose, I didn't say. Sorry. Okay, let me go to Color-Jones polynomial. But here, original definition is from representative theory, but I will introduce another way to obtain colored Jones polynomial. And here, the goal is to generalize Jones polynomial by modifying diagrams. What does it mean? In the previous page, I showed 2 ways to generalize the polynomial invariant. First one is change the equality. And second one is change the way change the space when we see the representations related to braid and its closure. But in this part, we don't want to. We don't want to change equality. We want to use Kauffman bracket, but want to generalize the Kauffman bracket and Jones polynomial by modifying diagrams. And here, the colored means, in some sense, can be understood in the following way. Here, we have a knot diagram. Then, how we modify diagram? From here, there is one way to obtain infinitely many link diagrams. It is draw parallels by using blackboard framing. And let us denote D1, D2, D3. Oops. And then we take Kauffman bracket to the n. Then clearly it is invariant under Rademaster move 2, 3, but not RM1. Actually, in some sense, it is quite clear. It is because originally Kauffman bracket is not invariant under Rademaster move 1. So let us see what happened when we apply Rademaster move 1. Before that, so firstly, let us see what happened for this one. Then if you calculate this one, you can get 8 to the 8, this one, minus 8 to the 8, nothing, plus 1. So here, if you remember this one, when we obtained for Kauffman bracket, we multiplied something with this one. So it was really simple. The happening by kink was really simple for Kauffman bracket. Just multiply one coefficient. So we resolved the problem by multiplying some coefficient additionally. But in this case, no. So, I mean, here, our good expectation is this one is equal to something multiply this one. But as you can see, it is not good. But if you modify this equality, then we can make it looks better. What does it mean? I move this one minus and equal to this one. If we change like this, then we can get such a thing. And in some sense, this is what this is the form which we wanted to obtain, right? So let's say ds2 is here left the same point same common character of left and right part is firstly there are parallels minus empty. So we take ds2 is d2 minus 1 empty. Here, for convenience, we remove 1 empty. Then when we apply kink, then for empty knot, there is no we don't need to care. It is empty. So we just need to kink for parallels. Then we just multiply 8 to the 8. Then let's say ds2 kink is equal to 8 to the 8 something ds2. We obtain such a equality. So instead of just parallel, by using ds2, to obtain is an invariant under right-dimensional rules, and we denoted by J2 Ka. This is called second colored Jones polynomial. Then, in this manner, we can see to obtain the invariant on the right-dimensional 1, 2, 3 by make parallels of D is not well. It is difficult, or this is not possible. Just by using parallel, we cannot obtain invariant under all right-dimensional rules. But by modifying it, instead of parallel, we do put -1 here. We can obtain invariant under right-dimensional rules, all right-dimensional rules. And here the point is, if we replace D2 by ds2, we can obtain such an equality. By kink, we just when we add or delete kink, we just need to multiply some coefficient 8 to the 8 to the sign. So by modifying it with rider and 8 to the 8, we can obtain invariant under right-dimensional rules. Then for dk, when you obtain parallels more and more, we need to find such a ds. So let me see. Let me state the question. For dk, for k bigger than or equal to 3, what is dk to obtain? So when we generalize our idea, we need to understand what we did for D2 and DS2. Then DS2 was such a thing. When we have a knot diagram like this, we make a band with blackboard framing. Oh, sorry, let me draw again. First step was make parallel on the band obtained by parallel blackboard framing and nothing. Here we do not put any red arc, so we get empty knot. So this was D2 minus 1 empty, we denoted by DS2. Then how we obtain this one? Actually, from for left diagram, we did such kind of thing. We just take a band, analysis like this, and put two parallel circles and put this one here in natural way. And in the same time, again, we get analysis and put nothing and put here. So if we say this summation is one element in some space, then we just put to the band obtained from the given diagram, and then we obtain the S2. And let's say this is S2. So let me write like this. Such a linear combination of links on analysis provides a linear combination of links obtained by them on the band for the given diagram. So here, the point is we put linear combination of links on the analysis to the band. Then we obtain linear combination of links again. So moreover, S2 is a kind of eigenvector of the operator. We change the band to this one. So here, if we want to see such kind of thing, we need to consider some to say linear combination and some eigenvector, whatever it is, to say such kind of thing, we need to consider a kind of vector space consisting of rings on the cylinder. So for that, I would like to introduce one notion which is called Kauffman bracket scheme module. Then what it is, let M be an oriented three-manifold, maybe but with boundary or not, and R a commutative ring with identity. Usually it is G to G or plus minus 1, Q, C, and let LFR be the set of ambient isotopy classes of framed rings on M. And now, instead of vector space, we consider a module generated by LFR with empty link. And now let's say S is a submodule of RLFR generated by the following equalities. Then S2 infinite M R is equal to R L F R S is called the Kauffman bracket scheme module. Here one comment is, in generator, as you see, well, we consider quotient module. So quotiented by S generated by this means this one is equal to this one plus this one, and this one is equal to plus this one. But here, why I checked like this, in three-manifold, it is not clear what is the trivial knot. So in three-manifold, trivial knot means a knot which bound a disk inside M. So if we have such a component which can bound a circle inside M, then it can be replaced by coefficient. And this is called Kauffman bracket scheme module. And in our case, we are interested in analysis. But to consider links, let's make let's thicken it by multiplying 0, 1. Then we can consider it as 2 infinite of this space. But in the Kauffman bracket scheme module of analysis times 0, 1, actually we can define multiplication and we can make skein algebra of this space denoted by S. This one. What does it mean? This is S2 infinite times I with multiplication by stacking links. Then what is a stacking links? Let's say we have 2 links inside analysis times I. Let's say here we have one knot, and here we have another knot. Then their multiplication is defined by literally stacking them. Then we put the first one on the upper part and remaining another one put here. By multiplying such a multiplication, we can obtain skein algebra of analysis times I. From here, we for simplicity we denote it by S analysis, SA analysis. Then as a theorem, we can see such a thing. SA analysis is infinite dimensional module spanned by 1, x squared, and so on. And here, what is x? X is just occurs this. So let's say to such an empty case 1, this one is x, this one is x squared, and so on. As a module, it is infinite dimensional module spanned by such an element. And then as an algebra, this is finitely generated by x. So SA analysis is isomorphic to C a to the plus minus 1 x to the plus minus x. And if you consider the definition of Kauffman bracket module, then it is quite clear, because when we have a link like this, if you have such a link, then it is equal to this one and this one with A plus A inverse. And by repeating this operation, in the end, we just obtain linear combinations of such a nothing or one circle, two circles, three circles, and so on. Moreover, by multiplication, we can see such a x squared, x cubed, or and so on are also generated by x. Then simply you can say this one is finitely generated by x, and actually it is equivalent to the polynomial ring with variable x with coefficient from a to the plus minus 1. And now, do you remember we wanted to obtain an algebraic a kind of vector space consisting of links on analysis, and this is that algebraic structure. And actually, it is isomorphic to this module, this algebra. And then, let me remind what we did. Here, firstly, we get linear combination, and we put them to the band. And we define that operation, which is called threading operation. Let's say D be a diagram of K, and P, X is element of skein algebra of analysis. Of course, this must be a polynomial with variable X. Then D, P, X is induced by a map. This analysis goes to this analysis. More precisely, if Px is equal to x to the n, then B dxn is a n parallel of E. And if Px is linear combination of psi, then dPx is sigma di dxi is equal to n. And we call this operation is threading operation. So as a remark, J2K8 was defined by a to the 8 minus rider d bracket dx squared minus 1. And finally, let us ask again, why dx to 2 minus worked? It was because when we have a let's see, this one is x squared minus 1, then x squared minus 1 gives a to the 8 of this one. That is, x squared minus 1 is an eigenvector for Rademacher move 1. Then for higher number, which polynomial will be eigenvector for y-dimensional move 1. It is Chebyshev polynomial of second type. It is defined by recurrence relations S0 x is equal to 1, S1 x is equal to x, Sn plus 1, x is equal to xSn, x minus Sn minus 1, x in SA, this one. And we usually denote it by such a diagram. On the analysis, one circle in the box with number n. Then, as a lemma, for right-dimensional 1, it satisfies such an equality, and as a corollary, if we define Jn, Ka by using Sn multiplying some coefficient with rider, then this is an invariant under right-dimensional moves, which is called nth colored Jones polynomial. And as an example, for trivial knot, Jn circle A is equal to minus 1 to the n, a to the 2n plus 2 minus a to the minus 2n minus 2, a to 2 minus a to the minus 2. In this manner, we can define n-squared Jones polynomial. Okay, I think time is almost finished, so let me write 2 or 3 sentences more. Here, first one, I little bit rush it, and maybe you are wonder why Chebyshev polynomial of second type works. If you are familiar with template Lie algebra, then Sn is the closure of Jones-Wenzel idempotent. And this element in template algebra have really good properties. By using that, we can show this lemma. Moreover, its closure satisfy the recurrence relation of Chebyshev polynomials of second type. So we use Chebyshev polynomial of second type. but I didn't say because if I explain it, I need to take weeks. So this one is the first remark. And secondly, why I wanted to introduce Color-Jones polynomial. Firstly, the first Jones polynomial is original Jones polynomial, and the colored Jones polynomial is called the color-Jones polynomial is known as the quantum invariant. Why? It is because the simplest reason is when as I said, color-Jones polynomial can be defined by representation by representation theory with quantum groups. More precisely, quantized version of Lie algebra of SL to C Lie group. So in some sense, it is called in that sense, it is called a quantum invariant. And in some sense, because the Jones polynomial was the first well-known quantum invariant. After that, many people worked with such invariants. Moreover, next time we will show that actually a little bit more extended version of color-Jones polynomial, which is Ruzhetikin 12 invariant, is actually invariant for three manifolds, or more precisely, oriented three manifolds. So next time I will talk how three manifolds are represented by knot diagrams and how we will define polynomial invariance by using such a representation by the knot diagrams for three manifolds. And that's all for today, I think. Thank you very much. Are there any questions?
Thank you, Kim, for such a wonderful talk. So I don't are there any question from the audience? Okay, I don't think there are any questions then. Okay, we'll stop here today.
Thank you very much.
Thanks again, Kim.